Thank you. Thank you, Richard. So it's indeed an honor to be introduced by Richard Rand. So the outset, I'd like to thank Professor Ivana Kovacek and Stefano Lenci for this opportunity to take part in this symposium. So this talk, as is mentioned, is not only dynamics of noise. So you heard a lot of talks throughout this meeting to do with stochastic dynamics and noise. This talk will have a different flavor. So I'm more interested in doing experiments and phenomena and how noise plays a role in influencing this phenomenon. So in terms of my journey through this topic, I should mention that my first exposure to noise, thanks to Professor Srinamachivaya, happened in 2002. He had an IUTAM Symposium in Nonlinear Stochastic Dynamics, which he had asked me to come listen to. And that's where I first started listening to noise, stochastic resonance, different phenomena. That's what started me on this journey. So I know this IUTAM Symposium in particular has many people who are fairly young in their careers. So perhaps for many of you, this could be a starting point to forge into different directions. So for this talk, I'll borrow material based on what I've done with my students and collaborators, Andrew Dick, Shiv Chakrabarti, C.D. Moore Jr., Edmund Perkins, Ramakrishnan, Salyu Telly, and Vipin Agarwal. I have some ongoing collaborations with Jim York and Miguel Sanjuan on partial control. We haven't written any papers yet, but we're fairly close to putting something together. So by and large, this work has been supported by NSF. So in terms of noise, this is a very brief introduction. It doesn't do justice to everything that you probably heard earlier, and you probably will hear later in this meeting. So noise, it's quite commonly used in digital signal processing as well as in biological systems. Noise is known to have a fairly beneficial effect. What you see in the cartoon illustrated up on the top is a case where a neuronal spiking happens every time the noise help you crosses a certain threshold. And the neuronal dynamics in this case can be described by monostable Duffing oscillators. So noise in this case helps you trigger the system to act in a certain way. Apart from that, it's also used in dithering and digital signal processing. So for us, I'm more interested in cases with a couple oscillator arrays as to what noise could do to dynamics. So here's an illustration of an array borrowed from the work of Alan Seaver, Masayoshi Sato in Japan, so where they actually looked at a couple oscillator array. What you see on this vertical axis is different cantilever oscillators, and what you see on the x-axis is time. So the darker the region, it means the amplitude for that particular response, the oscillator is larger. So in this case, energy is pumped into the system through the base, and what you see is energy is localized in one of the oscillators after a certain time. So the question for us is, if we have a periodic response such as this in a coupled oscillator array, how might one use noise to steer that location, or perhaps even suppress it, or induce it to shift to a different location? We're also interested in looking at how it may be used in other contexts, like flexible rotors, where we might have whirling motions. Could I take the system from one orbit and push it to another orbit of interest? One thing which you don't see in this chart, list of things, is trajectory control, which I'll allude to a little bit briefly as we go further. So in terms of questions, just to elaborate a little bit more as to what I said earlier. So I would like to use noise to study how I might suppress periodic responses like localization, or aperiodic responses, or shift a response from one branch of responses to another. As a trajectory control, if I have a trajectory that I'd like to keep in a certain region of state space, how might I use noise, or in the presence of noise, add controls to keep it within a certain region. So the system that I'd like to use to illustrate or find answers to these questions are three of those. It's a prototypical Duffing oscillator that you see out here. To elaborate a bit, an A from cantilever and a flexible rotor. These two are the macro scale, and this one is at a micro scale. So nevertheless, a phenomena cuts across length scales. So through this talk, what I'd like to show is noise could lead to amplification of response, could lead to energy transfer from one to another, or stabilization of a response or harmonic input. Or if you had a deterministic input plus noise, after your deterministic part is switched off, could the noise sustain the response for longer periods? And of course, the attempt to decide dynamics through introduction of noise. So you'll hear more about duffing later tomorrow, I presume. So this is the realization in the lab. Essentially, is a beam structure with a tip magnet. At the top is another magnet. So the south pole and the two face each other. So depending upon the spacing from too close to each other, then the upright position is unstable, and I have two stable positions either side. If they're fairly far away, then the upright position is still stable, so you can control the hardening or softening type of oscillator characteristics based on the separation out here, and that plays into these coefficients up in the top. So typically, this is a type of analysis we do for numerical work that we do. We take the governing equation, take the adiabatic elimination, that is the mass goes to, the limit is mass goes to 0, end up with the first order equation, and then put in this differential form so that I can deal with the differential in the noise, as W dot doesn't exist for noise. And then the question for us then is, if I had this bistable system, how do I control how much time it spends in each well? How do I choose the noise input so that way I know I would like for it not to stay all in one well, perhaps skip from one to another? So a question that came up for us, how do I determine this noise level? So one crack at it was to look at the mechanical system itself as a communication channel, and the input that you put in is on one side, the output is your response of the system. So if everything that I put on the input side comes out on the output side, the information rate would be equal to your Shannon entropy of the system. Of course, due to the response, the dynamics of the system, different anomalies are introduced, and the information rate turns out to be different than your actual Shannon entropy of the system itself. So this is a non-physical measure, at least for a mechanical system. For in other contexts, it could be interpreted, especially electrical systems, as a physical meaning. So in our case, let's suppose I am in the left well, so that will be a quantization of 0. The right will be 1. So if it's a communication channel, I'm basically transmitting 0, 1, 1, 0, depending on how much I'm spending in each well. But then you could calculate the information metric. The information metric shows a peak at a particular noise level. So without the noise, that's my input into a system. The response, that's your red is your system input, and blue is the oscillator output. That's basically in one well. But if I pick a noise level fairly close to this peak, then what you see is the noise shown in blue, the response in blue color, oscillates in one, skips to another, goes back to another well, comes back, switches back and forth. Whereas with too much noise, I end up spending too much time on one side or one oscillator. So this information metric is a fairly useful tool for us, at least in this case, to figure out how I can control the response to stay within a particular region, or in this case, from one well and then jump to another well and so forth. So again, staying with the duffing oscillator. So if I take a softening oscillator, let's see up at the top. So in this case, I have a system with natural frequency about 50 hertz. So in this graph that you see, this is about 50 hertz in the system. And I'm going to be operating somewhere close to 21 hertz, which is the left side of that. So I'm going to look at 3 illustrative cases. The first case where I don't have any noise. The second, until increasing levels of noise intensity. So the first case, this frequency, I picked this case because I have an aperiodic response. So that's your Poincaré section showing the fractal character. And if I increase the noise level, you see that the system response gets pushed to one side. Also response is, the amplitude level has come down a little bit towards one well. And then if I increase it further, I get shifted to the other well. So basically in this case, I have an aperiodic response, and then I'm using noise to move the system to either well and stabilize the system at that location. So the experiments that were conducted, going back to this illustration out here, is a cantilever structure, again, a tip magnet and another magnet whose location is fixed. I vary the spacing in between to realize a softening or a hardening characteristic. And again, the same experiment. So again, you have a chaotic response, and I could add noise to it to suppress it more or less to a cloud of points around my equilibrium point of my unforced system. So, this is a video captured the same thing in the experiments. If I were to play that, what you'll see is before noise is added, the system is in a chaotic mode of oscillation. As noise is added, you'll see it more coming towards straightening out, staying in the vertical position, lining up so that the upright position becomes a stable point of the system. So in this case, we showed how noise could be used to change completely the character of the response. You could also use noise to, if you had a hysteresis, like in this case, the jump locations. With noise, they are brought closer together, and with high level of noise, you could pretty much squash this hysteresis. And you see the same character in the experiments as well. So using noise, so you could transform the behavior of a nonlinear system, like in this case, to look more or less like a linear system. Now, of course, this is, in the physics literature, this is well known that hysteresis could be destroyed by using noise. So in this case, what you see is just an illustration for a Duffing oscillator. Now, so in this, switching a different system, so in this case, our interest again was in cantilever dynamics. I have a tip which is used to scan a sample. So I like to be as close to the sample as possible without penetrating the sample. So the question always that comes up is, how do I know when I've made contact with the sample? Especially the sample is delicate, you don't want to pierce the sample. So the question then is, could you use anything from dynamics that gives you an idea as to how close the tip is to the sample? So these are roughly the physical parameters of the system. The system has a first natural frequency around 12.74 kilohertz, and the second one around 78 kilohertz. And what we would like to do in this case is go around grazing contact of the system and see if we could use noise to figure out when it makes contact or not. So close to grazing contact, from just a little past grazing contact, the simulations predict that I have a period doubling in the system. That's your boundary at which it grazes and comes back. And that's a corresponding experimentally observed response. So in this case, the excitation frequency is not at the first bending frequency of the cantilever, which is typically common in AFM operations, but rather somewhere between the first and the second natural frequencies. So this 2.34 times that we found is again something that we found from macroscale experiments. The phenomena is universal. So if you did the discrete map analysis, what you'll find is close to grazing contact, you have period doubling both in the macroscale and in the microscale system. So the question is, if I come and operate the system somewhere out here, could I use noise to push it close to grazing contact, just past it, so that way I can detect the fact that I have grazing contact? So this is experiment without noise, harmonic excitation. That's your excitation frequency, that's your base excitation, that's your response, period doubling. And then with the noise, again, the noise level is fairly small. Just to give a sense of what does small mean out here, this is my base excitation plus the noise. You can hardly see the level of noise, but it's still discernible. With after introduction of the noise, you can see that you pick up your subharmonic, and this orbit has period double. So essentially, in this case, I'm close to grazing contact. I'm using noise to induce grazing contact. So that's right below, before the contact happens. If you have to follow the, so this is right at the point before the period doubling bifurcation happens, and the system is barely making contact. And if I take the shaker now, and if I, apart from a harmonic input. We also include a noise input out here. The question now is, can I have grazing contact between my tip and the other side? So these are macroscale experiments where I've replaced the AFM interactions that you see by interaction between two magnets. So roughly they give the same type of flavor. So with noise, you can see that I'm going to start making contact with a sample. So this is a case where noise has been used deliberately to find out when I have contact or not. In other experiments, we've also taken cases where there's sticking and used noise to pull the system out of the sticking region. So we have not taken this beyond this in our work, but I know Japan, the equivalent of NIST, AIST, they've taken this and they've developed their own technology for AFM scanning in their operations. Now, switching gears to localization. So in this case, what I'd like to do is talk a little bit about what noise does in coupled oscillator arrays, in particular localization in them. Localization in this case is a result of nonlinear discreteness, as many of you know about the Anderson effect, where you could have a set of linear oscillators, coupled oscillators, where the defect could lead to localization. By contrast, here I'm talking about nonlinear discreteness. These are simulations done by Burkolov in Moscow, in which he's done with 1D and 2D lattices to show localization with the lattice unharmonic. This is Princeton and Technion collaboration, which experimentally they saw photo optics, photonic lattices where you see localization in the peak and response, a localized region, and predicted as well by simulations. And this is another system which you saw a lot in this particular symposium in coupled pendula. So that's an analog in electrical systems, so Josephson junction arrays. Again, you can see localization in particular locations out here. This is closer to what I'll cover in the talk today. These are the AFM cantilevers, which I had mentioned before. Again, the site location is on the y-axis, the time is an x-axis. And after some time, energy is localized in one of the oscillators. So the question is, can I move this localization around? So the system, if you were to take a pair of oscillators, a long cantilever and a short cantilever, a long and a short, and you take the coupling, and you write out the equations. Essentially, you have an acceleration term, a dissipation term, a coupling term, a linear and nonlinear coupling term, and the excitation on the other side, which is because systems, all the oscillators are excited at the base of the system. All of them see the same excitation. Now, so in this case, you can go through for 100 oscillators. We went through, do some perturbation analysis. You could predict the localization location. So this is an oscillator where the localization happens. Right around it, you have this structure. There are different types of structures you could have when you talk about localization. So this is the particular structure that we focused on out here. And so the question is, can I move this localization around or suppress it in this chain of oscillators? So these are just rough numerical simulations without noise. If I see the localization at a different oscillator location, dies away, but in a particular location, 100 oscillators stays. This is the region where the excitation input is ramped up and kept at a certain value. And if the noise levels increase, then these localizers are pretty much killed. This is just brute force simulations. So we took the same set of systems, and then we thought maybe we'll generalize it to a larger array of oscillators. In that spirit, we took this chain of oscillators, and then we went through the mechanics, took those, put in state space form, as you saw for the Duffing oscillator, then the first order form, and then for the numerical integration, we used Euler-Maruyama scheme. And with that, again, you could predict without noise, with noise, and how localization is introduced. I had to be careful in calling this localization in the sense, in this case, all the oscillators are similar to each other. So its energy is concentrated at one particular location. However, so this, basically the proof of concept of what we saw before. And then we did the Fokker-Planck analysis, which is where you take the probability density equation, use the method of moments, get infinites at ODEs, truncate them, and do the finites at ODEs, and make some approximations. And then you can make some predictions. So if you do that again, we capture what happens with and without noise in terms of the energy concentration of the system. Again, in spirit, this agrees with the numerical integration that we did before. So the question then is, can we use noise to destroy localization like what you saw before in one of the slides? So to verify that, we did some experiments. So essentially, there's a set of 8 oscillators here. And each oscillator has a tip magnet, and there's also a magnet up on the top. So you have bistability. You could have bistable oscillators or monostable. And you also have a coupling spring that we don't show in this case up on the top. Out here, the whole system is driven by a shaker at the base. And we have PVDF films that we use to pick up the response of the system. I know there's a lot of interest in this Symposium energy harnessing. So if you were to take this PVDF film and harness energy, you'll probably get about 40 milliwatts of power. Very small. So in this case, so what I'd like for you to do is I'd like you to focus on the 4th oscillator. So this localization in this oscillator, that what we do is we'll destroy that localization by introducing noise. Okay. So essentially, what we've done in this case is we had a localized motion, a periodic motion, and then we added noise to the harmonic input that's being brought into the system, and the localization that we had in the 4th oscillator was destroyed by introduction of this noise. So we repeated these experiments in a different setting. So this was a collaboration with Kyoto, with Ichiro Takahashi at Kyoto University. So basically, he had a setup where we had a similar setup, a little different. Let me walk you through that. Essentially, cantilever structure, the permanent magnets, electromagnets at the bottom. And so the shaker actuation that you saw in our studies, you have a magnetic actuator that pushes the whole system. These are all coupled through this coupling rod. In this figure, although it's not shown, these are again 8 oscillators. There's localization in the 5th oscillator in this chain of 8 oscillators. So we repeated the same experiments we did at Maryland, at Kyoto in a different setup, but all those very similar in spirit. The cantilever beam with tip magnets, and the actuation is different. So what you see on the top left is if I where I have no noise, if I were to look at a localized oscillator, that would follow a typical Duffing oscillator profile that you say, which is similar, if you will, for a single oscillator. And then if you add noise, you see that response starts falling off after a certain region. And with a lot of noise, you come down, the response has a completely different character. So we excited the system at about 33 hertz. And so there was a localization before noise was added. So the first 10 seconds, you could say the darker region essentially indicates that my 5th oscillator there has all the energy concentrated in the response at that location. So after noise is added, the darker region fades away, saying the response localization is killed. And in this experiment, we basically pushed the localization, which is the 5th oscillator, to a couple of other locations. That's what has happened in the other case. So basically, in this case, for an array of 8 oscillators, like we saw in the previous case, we were able to kill the localization as well as move it to a different location. So the experiments, again, were conducted the same. To complement, you see same type of behavior or in terms of response curves. And you see the localizer is killed after some time with noise and can all be shifted to a different location. So essentially, so far what you're seeing is a case where I can either shift the periodic response from one location to another or completely eliminate that using noise. That's what we've done. So this is a little different setup compared to what you saw before. So in all the previous cases, the beam oscillators, you could pretty much, if they think in terms of structural dynamics, could project it down to one mode and look at it as a Duffing oscillator. So in this case, what we have is a little different system. We have a flexible rotor, which is, this is a couple of meters long. I have a disk, which is a rotor that spins, and then I have a borehole or a stator at the bottom. I have contact interactions between the rotor and the stator, and I have a slip ring out here to pick up the strain gauge responses from my rotor. And of course, I have an encoder on the top and a servo motor to provide my torque input for the system, and a camera here to pick up what happens within the stator. So this setup, if you will, it can be used to understand what happens between two stabilizers and a drill string that you saw on the talks yesterday. Of course, there's no cutting action in this case. So in these operations, backward rolling is something that you'd like to avoid. So the question now is, with noise, can I move the response around from one response branch to another? So if I take the system, if I did one experiment where I had forward whirling, then I do backward whirling. In the forward whirling case, basically the rotor is spinning in the same direction as my input torque. The backward whirling, which is a little bit more violent, the rotor is spinning in the opposite direction. So if I took that rotor and projected it down to a Jeff-Cott rotor model and did another projection down to a torsion response oscillator model, and then you can plot this frequency response curve where without contact, the frequency response would follow up on the gray lines and come down, and then you'd go down. With contact, you'll have additional branches. The red would be your backward whirling branch, and the blue would be a forward whirling branch. So you pretty much have two forward whirling branches. So the question is, can I use noise to steer my response from either a large amplitude forward whirling to a lower amplitude forward whirling, or from backward whirling branch to a forward whirling branch? So that's what I would like to know. So if I could do that in practice, then I could add the noise input to my torque input, and then move my response to something which is more desirable for my system. So these are experiments where this is my torque input. This is a servo motor on the top. Then you add noise to it. The noise is switched off. So what happens in this case is I have a forward whirling motion, and I'm able to use noise to kick it to a backward whirling motion. So I've basically gone from this response branch to upper response branch. Of course, in practice, this is not something I would like to do. I would like to go the other way. But so far in the experiment, it's the best we could do with this particular setup. And then in this case is another one where we had whirling without contact, and then one forward whirling branch to another. Again, using noise, you go from one forward whirling branch to another forward whirling branch. So the open questions as to how long this noise should be switched on, what should be the amplitude, is there a certain threshold beyond which this works? So those are questions we have to answer yet. So we did do some studies to complement experiments. So essentially, we took the rotor, and we projected it down to three states, two translateral directions, lateral vibrations, and one torsional state, and that led to those equations right here. And you also have another equation governing on the top. And then you have your backward EMF and other things for the motor accounted for in the loop out here. And the noise is introduced through my torque input into the system. So you could take this system of equations and do Euler-Maruyama simulations again with them. If you do that, you could show that I could use noise to, if I were to start with the case without, of course, these are simulations, so it's a lot cleaner. So without noise, and there's a region where noise is included, and then you could kill the response. You can go from a forward whirling case to a backward whirling case. So it matches very well with what we saw in the experiments. Again, the case of interest for us where we could go from backward whirling to a forward whirling, we have not been successful so far. So that's something that we still have to explore as to how that's possible. If we can do that, so typically when you do drilling, you would like to avoid the contact with your borehole. You'd like to stay very close to the center of the bore well. So the question now is, how could you possibly do that? So what you've seen in the talk today is I gave you different aspects of what we've done with noise. Essentially, some of these could be tools for further studies in other systems. One is the Shannon information rate and how it might be used to pick up your right noise level. The Fokker-Planck formalism, both for the single oscillator case, AFM cantilever, as for the coupled oscillator arrays, how might one use that to understand what noise does to your system. Through experiments as well as simulation, you're able to show how noise can be steered to different regions. Of course, noise enhanced performance could be useful for many different systems, as you only saw a glimpse of it in the talk today. And I do think at least, of course, I have a biased viewpoint. For paradigm shifts, nonlinear phenomena are quite important to consider. In ongoing work, we're currently looking at localizations and system cyclic symmetry. So the question is, if you took the bladed disk with many blades, typically localization happens in a certain region. So the question is, could you use noise in those cases to move the localization away or suppress it? So it will be taking those systems that we studied before and introducing cyclic symmetry and studying what happens in those cases. In another direction, I think we're also looking at trajectory control. So if I were to work with this cartoon out here, if I imagine my response is in this region out here, I would like for the response to stay in this region without escaping to another solution. So how can I use noise or some form of input to keep my system within that particular region itself? So that's what happens in the case of the control. So in the experiments that you saw with the Duffing oscillator before, this is one example of what happens. So if I move it to a chaotic region, so it shows transient chaos before it comes out and escapes to a periodic response. So the question is, with control, can I still keep it in a chaotic regime? So that's the type of question we'd like to answer. So we have done some studies with Duffing oscillator as a prototype. Again, in this case, for particular parameters, you have period 1, period 3, apart from a chaotic response. So how do I keep my system in the chaotic response region without moving to P1 or P3? So the different things you could do, we have done following what others have done. We've looked at partial control. This is the mechanics of it. You basically take your system with noise, and then you apply control in discrete steps, and this you do it on the Poincare map. And then it's a question of how you pick your bounded inputs to keep your response within this particular region. So that's pretty much where we are today. This is further illustration of the same. In this case, this is a sculpting algorithm where basically without an input, I basically bounce outside the region with the control. I'll bring it back inside. So I'd like to keep it within a safe region. And what you see out here is the blue. The color region is where I'd like to stay. And as I go through different iterations, you sculpt away portions that you want to keep, knowing that your trajectory within that region will stay in that particular region. So this is ongoing work. We're also trying to do it experimentally. We have some delay problems in the experiments, but that's pretty much where we are today. And this has nothing to do with noise, but more a fluid structure simulation of a flapping airfoil. That leads to a question mark if you wait long enough. Thank you.